I think we ought to be able to get a manned flight to the moon within this century anyhow.
Well, thank you very much indeed. So the engineers, just like the astronomer we spoke to, seem pretty confident about space travel. But what about man himself? Are the doctors sure that man will be able to survive in outer space? Now, this is the special study of a doctor at the RAF Institute of Aviation at Farnborough.
Now remember, we're thinking in terms of putting a man inside this rocket, and that gives rise to quite a few medical problems. So let's go back to the beginning again, the takeoff. Now we know we can fasten the man up inside his cabin, so that he takes his environment with him, his terrestrial environment, that is, the air he breathes, his food, and so on. But what about the accelerations of takeoff, and later the the zero G, the absence of gravity? We know a great deal about the effects of these accelerations on the human body, and we study them on the human centrifuge. We have a film here showing the operation of the centrifuge. The arm which rotates carries a cabin at the end in which the subject sits. As it rotates, it produces a centrifugal force like an increased force of gravity. In effect, the man gets heavier. In the case you're about to see, the subject will be stressed to a force of about 5G, that is 5 times the force of gravity. The subject is now strapping himself into the seat, and I'd like to add that this is the sort of sensation all pilots experience during flight, and it doesn't produce any more stress than, say, being in a rugby scrum. The centrifuge is now rotating at the speed equivalent to 5G, and you can see the effect of this increased gravitational force on the subject now. It's coming on. It takes considerable effort to overcome this load. Of course, if the force lasted several minutes, he would have to be lying down. He can't do much whilst this force is on him. Physical movement is almost impossible. And what we have done, we put a room at the end of this arm so that we can observe the effects of increased gravitational forces on subjects whilst they try to move around. The controller is now ready to start the centrifuge again, this time with the subject moving across this end barrier or room. With the centrifuge stationary, it has no problem at all. It's quite easy. When it's rotating to produce 2G, that is twice the force of gravity, his body is twice as heavy, and you can see the struggle he has to move. It is now a considerable physical effort for him. He struggles back to his original position. The same sequence now at 3G, 3 times the force of gravity. This is the force he would experience if he were a space traveller and he'd landed on Jupiter. Jupiter is a larger planet than the Earth, and in consequence has a much larger gravity. You can see he can hardly move at all under the force of 3G. In the next case, where I was a subject, you can see, starting feet first, it was impossible to make any progress at all. The body was pinned up against this end barrier. But for the takeoff in rocket flight, with automatic controls, there shouldn't be any problem, provided any effort you required of the man was done by minute finger movements. Now what about the other stresses? Well, there is the absence of stress with 0G, no gravity at all. At some period in the rocket flight, everything will be stationary, weightless, and still. No gravity at all. We have a film here of the effect of 0G on some mice. Here you see the mice being prepared to be sent up in this high altitude rocket. They were placed in little containers inside the rocket. Now, at the top of the rocket's flight, whilst it was falling, there wouldn't be any gravity exerted on these mice. There it is, on its way up. 0G has affected their balance. They are disorientated. Now, a sense organ inside the ear normally gives us our sense of balance when gravity acts on it. One of the mice had this sense organ destroyed, and he wasn't bothered about 0G. He'd learned with practice to use his eyes alone to give him a sense of balance. Here are the mice after the run, quite fit and healthy. So with the man, we would be faced with this problem of disorientation. Here's a monkey. This is the highest animal in the world. He's been up in one of these rockets. Problem of disorientation with the man, and also problem with moving his limbs. His limbs wouldn't go where he wanted them because they were weightless. Again, under 0 G, our body wouldn't be able to regulate its temperature. Normally, the body is continually producing heat. And one of the ways in which we control this heat production is by losing heat by air convection. Here you see convection currents of air rising from the hand and carrying heat away. This effect would not be observed under 0 G conditions. It depends on gravity, because the air next to the skin gets less dense, less heavy, and therefore rises. We could minimize this effect by use of an air ventilated suit. Here is such a suit. The air enters this suit by this pipe and is distributed over the body, and this suit is worn next to the skin. This would cool the man. So it is one solution to this particular problem. Whilst we're discussing this air circulation, it's an air problem, there's also something else. Dust wouldn't settle. Bits of fluff, bits of wire, anything that happened to be loose would float in the air, and the man would have a serious risk of inhaling these foreign bodies into his mouth. Again, the body produces very toxic substances in small quantities, gases and so on from the bowel. And chemical extraction of these on the long-term project would be very, very difficult. In fact, an explosive air mixture could result after several weeks or months in a confined space. Other body functions depend on gravity, drainage of tears from the eyes and so on. And again, with so little effort required for whole body movement, you can understand that after a period of weeks or months, the person would very rapidly lose his muscular power and get weak, just as if he'd been ill in bed for a long time. Again, his heart would get weak, and you can imagine the space traveler, when he landed on his other planet, as soon as gravity exerted itself, as soon as he tried to stand up, he'd fall down in a faint. But I think we should now consider one of the most important accessories of such a space flight. That is the space suit.
Well, Doctor, that's just what I want to ask you about. This forerunner of the space suit developed for the RAF, which we're now going to see publicly for the first time. Just how big a step forward is it?
Well, there's a very long step between the partial pressure suit, which has been shown before, and this particular suit you see now. Perhaps we can have this inflated and you can see the action. See, space is a vacuum and the suit has to be pressurized.
I think it looks like every boy's idea of a real spacesuit.
Can you move around?
Could you take it off?
One of the most difficult engineering problems in designing such a suit is to provide an adequate range of physical movement whilst the man is pressurized.
Well, I can see you seem to move around all right. Were you uncomfortable? You're sweating furiously now, but were you really uncomfortable in it?
I was a little hot. I think the reason there is that if you are hot and you don't get sufficient ventilation, then of course you just sweat and get even worse.
Yes, but what exactly have been the biggest problems you've had to overcome to live in a kind of a vacuum, which you obviously must have done to test this suit out?
Well, if you're going to live in a vacuum, you have to breathe oxygen as a technical convenience, yet it would save enormously if you can pressurize yourself with air. There you have two systems and, as you see, two pipes leading to me.
Mm-hmm.
Maintaining a balance between those two so that you don't become uncomfortable is quite a problem. Not only that, but you have the pressurization which causes your limbs to tend to stiffen out, and the bending them, of course, might be difficult with bad design.
This
Well,
suit
yes.
actually would only be used in an emergency. Normally he'd be in his space cabin.
But
And
I
it wouldn't
don't-
protect...
yes. Go on, so carry
It
on.
wouldn't protect him again from cosmic radiation
I
at
see.
all.
But there's one, you've obviously studied, I mean, the effects of high altitude flying on men. Do you see any biological reason why man shouldn't be able to exist in outer space?
I don't see... well, I can say with confidence that there is no single medical factor which prevents manned space travel.
Well, that's a pretty categorical statement and said very confidently. Thank you very much. Now, there's one group of people who've come very much into the picture since the launching of the Russian satellite, and that's those who belong to the British Interplanetary Society. Now, some people think that the members of it are too visionary and the society is too premature. But we have one member of the society who has this answer to give.
Well, the British Interplanetary Society most certainly isn't premature, and I think there's a very good parallel to that in the Royal Aeronautical Society, which was formed long before aeroplanes flew. In fact, it was long after the formation of that society that one famous American astronomer proved to his own satisfaction that aeroplanes could never fly at all. Well, nobody in the British Interplanetary Society underestimates the difficulties, but they have made very considerable contributions to what has been going on, and in particular, a good deal of the early theoretical work on Earth's satellite was carried out by its members. Many members of the society hold official positions in government establishments, and it must be realized that in these days, all practical rocket research must be done at government level. That's partly because of the tremendous cost of the equipment, and partly because of security, because in these days, so much rocket research is being misdirected towards military requirements.
Well, that was Patrick Moore, who is a fellow of the British Interplanetary Society, and I must say, Mr. Moore, you're a very spirited protagonist of your society. Now, by way of summing up, I'm going to talk to one of the most distinguished physicists in the country, Sir Edward Bullard, who was formerly director of the National Physical Laboratory and who is now at Cambridge University. Now, I know you've been following this program very closely, Sir Edward. What do you consider to be the biggest problem that has to be solved?
Well, I think the biggest problem's been solved already. The biggest problem is getting off the ground and through the air and into the orbit. This requires these enormous engines. Once you're in your orbit, you've got time to think what you're doing next, and you don't require these very great forces, and all kinds of possibilities open up. I think it's impossible to exaggerate the importance of the success of recent work in America and Russia.
Mm-hmm. But what do you think are the real possibilities of interplanetary travel? For example, do you agree with Sir Harold Spencer Jones that whereas it would be possible to get to the moon, it isn't possible in the foreseeable future, if at all possible, to get to planets like Mars and Venus?
Well, you know, I don't agree. What Sir Harold said, in effect, was that if you go on a long journey, you need a lot of luggage, and therefore your rockets would have to be very large and carry a lot of odds and ends. Well, this is a problem of structures and fuel, and primarily a problem of fuel, and one can see all sorts of possibilities of improved fuels. It seems very unlikely that the one we've got now, petrol and oxygen, is the best. There are many others which we haven't time to talk about tonight, and some very peculiar ones. For example, I recently saw in America small bits of gas kicked out at 300 kilometers a second. And this kind of thing opens enormous possibilities, I think, for the next step from the satellite.
Nuclear power?
I don't know, really. It's a difficult one. I think there are other things will come first. I don't think the first. I think we'll get along without it for some time.
Sir Edward, it's been suggested in more than one quarter that the main advantages of travel to outer space are military ones. Do you agree with that view?
Well, I am dubious if the military ones are an advantage.
Yes, so am I.
But there certainly are civilian advantages of a kind. If you could look at the Earth's atmosphere from the outside, you could follow the weather systems and get, I think, very much improved weather forecasts. You could get the pleasures of looking at the American television from a relay station and a satellite, and vice versa. But these are rather minor things. And, you know, I don't really believe that these great enterprises depend on a delicate balance of gain and loss. I think that to do these projects, you've got to have an emotional drive to do them. That, in a sense, they're things of the spirit that you've got to feel that you want to do them. It's rather like the Egyptians building the pyramids. The pyramids were obviously no good, but they built them, and I think this may be our pyramid.
I see. Well, thank you very much indeed, Sir Edward. Well, all through this program, I've marveled at the confidence of the speakers, and I'm also wondering if there isn't someone among you now who isn't going to be the first person to step on the moon. Good night.